Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 5.4. A slurry contains crystal of copper sulfate pentahydrate with a specific gravity of 2.3, suspended in an aqueous copper sulfate solution. The liquid specific gravity is 2.2. A sensitive transducer is used to measure the pressure difference, delta P in pascals, between 2 points in the sample container separated by a vertical distance of h meters. The reading is in turn used to determine the mass fraction of crystals in the slurry. In crystals, kilograms of crystals per kilograms of slurry. Okay, and then they have a little picture here. I tried to replicate there. Part A, derive an expression for the transducer reading, delta P in pascals, in terms of the overall slurry density, assuming that the pressure head formula of chapter 3, pressure equals P naught plus rho GH, is valid for this two-phase system. Okay, so they're saying, assume that this is valid for this system. Okay, so we've got this chemical, that's the density, then we've got our density here of the liquid. What did I spell there? Sorry, this is the liquid. Must have been writing too fast. That's the density of the liquid, okay. Density of the liquid. Delta pH is in pascals, okay. And then we've got weight fractions. I always do my weight fractions with a W. In the book they use an X. It helps me keep things separate to do weight fractions as a W. Okay, so this is the mass fraction of the crystals in the slurry. Okay, if this function describes the system well, then we need to know what the pressure is here, and we need to know what the pressure is here. Okay? So delta P is equal to pressure 1 minus pressure 2. So this would be pressure 2, and this would be pressure 1. Okay? So P naught is the pressure at the reference plane. So my reference plane is the top of the liquid, okay? The top of where the liquid starts, right at that interface between the gas and the liquid. That's where my reference pressure is. So reference pressure plus rho GH, where H is 2 right here, since this is 2, minus our reference pressure minus rho GH from pressure 1, okay? So that's what delta P is. So these reference pressures cancel out, and we're just left with rho G delta H1 minus H2 delta H, okay? That's what delta means, P1 minus P2, H1 minus H2. Okay, so this is our function for determining the pressure transducer. It is related to the density of the slurry, okay? And if the density of the slurry is related to the weight fraction, then we've got a function there that we can determine weight fraction from. Okay. Part B, validate the following expression relating the overall slurry density to the liquid and solid crystal densities and the mass fraction of crystals in the slurry. Okay, so it's telling us to validate this equation. Insert units for all variables as a suggestion. So I don't really understand for this part what they mean to validate what it is. In my mind, validate means you make a set of assumptions and then you validate it by writing down what the assumption is and then kind of deriving the expression to say, like, yeah, this expression is rooted in these assumptions. That's kind of what validate means to me. I don't understand what they mean by insert units for all the variables. Well, I mean, I know what they mean by that, but I don't see how that relates to how you would validate the thing, okay? Because I could make up any equation and just put units in it and then make the units cancel out by, shifting things around. That doesn't mean that the equation actually describes a system very well. So I'm not exactly sure what they mean by that, but this is how you would derive this expression. If you assume that there's just a two-component system there, then and you assume that the volume is additive, then this expression is correct. Okay. Part C. Suppose 175 kilograms of the slurry is placed in the sample container with H equals 0.2 meters and a transducer reading delta P equals 2,775 pascals is obtained. Calculate 1. The density of the slurry, 2. The weight fraction of the crystal, 3. The total slurry volume, 4. The mass of crystals in the slurry, 5. The mass of anhydrous copper sulfate, that's copper sulfate without water, in the crystals, 5. The mass of liquid solution, and 6. The volume of liquid solution. Okay, so they gave us this. We know what the density, or what the acceleration due to gravity is. I just use the value that they gave in the book. That changes obviously depending on where you live, so I'm just using the one they have in the book. Then we've got our equation here, our chemical equation here. Based on that equation, we rewrite it for the density of the slurry, and because we have these values and we know what the acceleration due to gravity is, we can calculate that the density of the slurry is this value, okay? Based on that density, because we know that density, we can solve for the weight fraction of the crystal, okay? So weight fraction of crystal, that's our very first thing that they asked us. Now we want to know what the volume of the slurry is. Well, we know what the density of the slurry is, and we know the mass of the slurry because they gave it to us. So that's the volume of the slurry. Okay. Once we know the mass of the slurry and the weight fraction of the slurry, we know the total mass of the crystals in the slurry. Okay. Then they asked us, okay, now we want to know what the anhydrous copper sulfate concentration is. Okay, for this, we do need to know the chemical equation, right? So we write down what the chemical equation is. What process are they doing? Well, they're removing all the water from the crystal, and they just want to know what this is, okay? So dry refers to this, wet refers to this, okay? And then this is just for water, okay? So if we have this much mass of wet crystal going in, this is the molar mass, so we have this many moles of wet crystal. There's a 1-to-1 ratio of copper sulfate to wet crystal, okay? So dry to wet, there's 1-to-1 ratio. So moles of dry has this mass, okay? So then all of these units cancel out and we're just left with mass of the dry, which is the copper sulfate crystal, okay? And this is the mass of the dry copper sulfate. It's a little bit lighter, should be lighter, right? Because we're removing water from this, okay? So the mass of the liquid in the slurry, well, we just want to know what the mass fraction of liquid is. The mass fraction of liquid is equal to 1 minus the mass fraction of crystal, okay? So that is the total mass of liquid. What's the volume of liquid? Well, that's the mass of the liquid divided by the density of the liquid, and they gave us the density, so there you go. That is the volume of the liquid. Okay, so for part D, write a spreadsheet program to generate a calibration curve of the weight fraction of the crystal versus delta P for this device. Take as inputs the density of the crystal, the density of the liquid, and H, or delta H in our case. and calculate delta P in pascals for a given weight fraction. The set of weight fractions is 0, 0.05, 0.1, all the way up to 0.6, following that pattern. Okay. Run the program for the parameter values in this problem, so given all the parameters that they gave to us, and see if your answers that we got for delta P lands on the line that you created using your program. So you're just basically double checking your answer, okay? So it says to verify that the weight fraction corresponding to the delta P of 2775 pascals on the calibration curve corresponds to the value calculated in part C, like what we did. Okay, so what I did here is like, hey, I don't really need to do a whole spreadsheet. I mean, I did end up doing it, but I just solved for, okay, we've got our delta P here, and we've got our density there, and the given value that they gave to us, okay, right? So what I want is a function delta P equals some function of the weight fraction, right? That's what I want, because they gave us a bunch of weight fractions, and they said calculated delta P based off of that. Okay, so now I'm just going to substitute in our functions up here until I get something that says delta P equals a function of this with everything else being known. Okay, so I took this function and I changed it so that it was the inverse, basically. And we know all of these values except for that's our variable, right? So that's perfect. That's exactly what we wanted. So we just put this into this function, and now we have that function that is just in terms of the variable that we wanted, right? So then I just plotted that up, given all of the plots that we wanted. So if you take a look at this figure here, this figure has all of those points that they asked for, and then that red point there is the point that we calculated in part C, and you see that lines up exactly right on the line like what we were thinking. So yes, this does indeed work. Verified. Okay. Then part E, it says derive the expression in part B. Take a basis of 1 kilogram of so it's saying to take a basis of 1 kilogram. We don't need to do that. And use the fact that the volumes of the crystals and liquid are additive. Okay, so volumes are additive, basically, is what we're saying, right? We already did this, right? We already did that. We assumed that the volumes are additive, and we already derived the expression. We did that in part B. So that was the part that I was kind of confused about. I was like, hey, I don't know what the difference between validating and deriving is in this case. Like, it's kind of ambiguous as to what they mean. And if you're deriving something, you don't need to take a basis, because if you take a basis of something, you're only proving it for that one case. So we don't need to take a basis of anything. We can just derive it. So we can prove it for all the cases instead of just the one case. Okay, so this is the answer to part B and the answer to part E. Sorry, I don't have a better answer for you for part B. I'm not exactly sure what they meant. I mean, if you're just doing a unit analysis, you can say like, okay, the density, this is units of inverse density, this is units of inverse density, and this is units of inverse density. If you add these two together, you get inverse density. And yes, all the units work out. So that's the only other way I could think of doing part B. So there you go. That's the other part of part B. You did a unit analysis on it. Okay. Well, that is it for problem number 5.4. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.